The world's water crisis can be solved by making deep-sea water drinkable. What if the ocean's depths held a solution to the world's expanding water crisis? The concept of converting saltwater into potable freshwater has long been dogged by exorbitant expenses, ecological issues, and energy-intensive procedures. But a new technique called deep-sea reverse osmosis, DSRO, is changing the rules. This method provides a more environmentally friendly and energy-efficient method of producing freshwater by utilizing the tremendous natural pressure present at ocean depths. Imagine a future in which coastal cities suffering from drought may rely less on overtaxed rivers and aquifers and instead have access to the deep sea's enormous, unrealized potential. Beyond science fiction, it is changing. With its more economical and environmentally friendly solutions, DSRO is revolutionizing the way we think about desalination. You'll learn how this cutting-edge method can cut energy use by as much as 40%, stop hazardous brine from leaking, and even work with renewable energy sources like offshore wind farms. Despite its great promise, DSRO has drawbacks. The road ahead is as deep as the waters it aims to capture, from the huge upfront costs to the logistical challenges of deep-sea infrastructure. Is this a piece of a much bigger puzzle, or the secret to a more sustainable water future? Let's explore this technology's depths and possibilities. Quantum leap of deep-sea desalination. When compared to conventional desalination, deep-sea reverse osmosis, which uses natural ocean pressure at depths of 400 meters or more, can reduce energy consumption by up to 40%. By generating low salinity waste, doing away with the need for chemical pretreatment, and drastically lowering brine discharge that damages marine habitats, DSRO mitigates its negative environmental effects. Compact DSRO systems are perfect for crowded coastal locations with limited area because they use 80 to 95% less land than traditional desalination. Advanced filtering systems and real-time monitoring are examples of technological advancements that improve the DSRO's operational sustainability, dependability, and efficiency. DSRO devices can lessen dependency on fossil fuels and fight climate change by integrating with renewable energy sources like offshore wind or solar. The increasing water scarcity problem. One of the most urgent issues facing the world today is water scarcity, which is exacerbated by factors including population increase, fast urbanization, and climate change. Traditional water supplies, including rivers, lakes, and aquifers, are under tremendous strain due to the protracted and severe droughts that are occurring in many areas, including sections of the southwestern United States. The growing demand for freshwater is becoming too much for these sources to supply. Desalination has consequently emerged as a vital instrument in the fight against water scarcity. But there are some serious problems with traditional desalination techniques, which makes it necessary to look into more environmentally friendly options. Traditional desalination's drawbacks. Despite their widespread use, conventional desalination systems like land-based reverse osmosis, RO, have a number of drawbacks. These systems use a lot of energy and are mostly dependent on fossil fuels, which raise carbon emissions and worsen climate change. Additionally, a byproduct of the operation is concentrated brine, which is frequently released back into the ocean. This brine threatens biodiversity and disturbs marine ecosystems due to its high salinity and chemical content. Traditional desalination methods that involve chemical pretreatment procedures also present additional environmental hazards, including the possibility of chemical pollution. These drawbacks emphasize how urgently creative and sustainable desalination methods are needed. What is unique about deep-sea reverse osmosis? By harnessing the natural pressure present at ocean depths of 400 meters or more, DSRO provides a completely new method of desalination. Compared to conventional techniques, this pressure can save up to 40% on the energy needed to force seawater through filtration membranes. DSRO processes seawater directly at depth using specially designed pods positioned on the seafloor, as opposed to depending on expansive land-based facilities. These pods pump freshwater to the surface and consume 80 to 95% less land than conventional systems. DSRO is very useful in crowded coastal locations or urban areas with limited space because of its small size. The benefits of DSRO for the environment. The decreased environmental impact of DSRO is one of its most alluring features. By generating low salinity waste, which is significantly less detrimental to marine environments than other desalination techniques, DSRO reduces the amount of brine produced. Furthermore, chemical pretreatment is not necessary in the deep-sea environment due to its naturally low biological activity, which lowers the risk of chemical pollution. By tackling these environmental issues, DSRO supports international initiatives to save marine life and create sustainable water management techniques. As a result, it is a freshwater production technology that is more environmentally friendly. The progress driving DSRO. Modern technological advancements that guarantee DSRO's dependability and efficacy are the foundation of its success. Sophisticated filtration mechanisms that are intended to stop membrane fouling and provide steady performance over time are among its primary features. Technologies for tracking operational efficiency in real time that enable preventative maintenance and save downtime. These developments reduce maintenance costs and disturbances to marine life by enabling DSRO pods to function efficiently for longer periods of time. DSRO strikes a balance between environmental sustainability and operational effectiveness by utilizing these technologies, including renewable energy. DSRO systems can be linked to renewable energy sources like solar or offshore wind farms to increase their sustainability even more. This combination encourages global efforts to switch to renewable energy sources and lessens dependency on fossil fuels. Coastal communities may be able to provide a more sustainable and reliable water supply by combining DSRO with renewable energy. In addition to lessening desalination's detrimental environmental effects, this integration helps achieve more general climate change mitigation objectives. Advancement and prospects for the future. The viability and efficiency of DSRO have already been shown by pilot projects, opening the door for commercial-scale operations, which are anticipated to start by 2028. These advancements mark a major advancement in environmentally friendly desalination techniques. But there are still difficulties. Two significant obstacles to broad adoption are the high upfront costs of DSRO systems and the logistical challenges of setting up and maintaining deep-sea infrastructure. Furthermore, DSRO can't adequately handle water constraints in inland locations because it is best suited for coastal regions. Other tactics, like water conservation, wastewater reuse, and cutting-edge inland water management technology, must be used in conjunction with DSRO to provide a complete solution. Building a sustainable water future. In the battle against the global water crisis, DSRO is a significant advancement, especially for coastal regions that are extremely water scarce. Through the integration of renewable energy sources, energy conservation, and environmental preservation, this system provides a practical and effective freshwater production option. It is not a standalone solution, though. To guarantee a secure and sustainable water future for all, broader water management techniques are needed, including conservation, reuse, and the creation of creative inland solutions. The promise of DSRO is found in its capacity to support these initiatives and aid in the creation of a more robust and sustainable global water system. How does deep-sea reverse osmosis desalination work? Deep-sea reverse osmosis desalination is a process that uses the pressure found in deep ocean environments to help desalinate seawater through reverse osmosis, reducing the energy needed to drive the process. It is a form of pressure-retarded osmosis or deep-sea assisted RO, and is still largely experimental or in pilot stages. Here's a breakdown of how it works. Basic principle of reverse osmosis. RO is a process where saline water is pushed through a semi-permeable membrane that allows water molecules through but blocks salts and other impurities. Normal RO systems require high-pressure pumps, typically 50 to 80 bar, to overcome the osmotic pressure of seawater and force water through the membrane. What makes deep-sea RO different? In deep-sea RO systems, natural hydrostatic pressure in the ocean at depths of 600 to 1,000 meters or more is harnessed instead of or in addition to mechanical pumps. Pressure at these depths can reach 60 to 100 bar, which is suitable for RO. How it works? Deployment. A desalination capsule or module containing RO membranes is lowered to deep sea levels where natural water pressure is high. It is tethered to the surface by a hose or cable for communication, intake, and water return. Desalination. Seawater at that depth naturally enters the RO membranes due to the surrounding pressure. Freshwater passes through the membrane, while salt and other impurities are left behind in the brine. Water recovery. The permeate freshwater is pumped or floats back to the surface via a buoyant line or low-energy pump. Advantages. Reduced energy consumption. No need for high-pressure pumps at the surface. Lower carbon emissions, especially if powered by renewable energy or ocean thermal energy. Less surface footprint, smaller land-based infrastructure required. Challenges. Maintenance and fouling. Difficult to access and clean or repair equipment deep underwater. Biofouling and corrosion. Harsh deep-sea environments can degrade membranes and metal components. High initial costs. Specialized materials and deep-sea engineering are expensive. Water transport. Efficiently bringing fresh water back to shore or users remains a challenge. Current status. While promising for remote or island areas with deep nearby ocean and limited energy infrastructure, deep-sea RO desalination is currently in the research or pilot phase. Japan and South Korea have been leaders in testing prototypes of this approach. Deep-sea reverse osmosis RO desalination is an innovative approach to producing freshwater from seawater by utilizing the natural pressure found at great ocean depths to drive the reverse osmosis process. Unlike conventional desalination systems that rely heavily on high-pressure pumps to force seawater through membranes, deep-sea RO uses the hydrostatic pressure of the deep ocean to achieve the same effect, potentially offering a more energy-efficient alternative. Understanding conventional reverse osmosis desalination. In traditional reverse osmosis desalination systems, seawater is pressurized using mechanical pumps to overcome its natural osmotic pressure. This pressure, typically in the range of 50 to 80 bar, is necessary to push water molecules through a semi-permeable membrane. The membrane allows only fresh water to pass while rejecting salts, minerals, and other impurities. However, generating this pressure requires significant energy input, making conventional RO systems energy-intensive and costly, especially in regions lacking cheap electricity. Principle of deep-sea reverse osmosis. Deep-sea RO desalination takes advantage of the fact that hydrostatic pressure increases with ocean depth. At around 600 to 1,000 meters below sea level, the ambient pressure naturally reaches 60 to 100 bar, approximately equivalent to the pressure required for seawater reverse osmosis. By placing RO membrane systems at these depths, the surrounding pressure can be used to drive the desalination process without relying on energy-intensive pumps. How deep-sea reverse osmosis works. The process of deep-sea RO desalination can be broken down into the following steps. Deployment of RO modules, specially designed RO desalination capsules or modules, containing reverse osmosis membranes, are deployed from the surface and lowered to deep ocean depths, typically 600 meters or more. These units are connected to the surface via pipes or flexible hoses that allow for the flow of water and data communication. Intake and pressurization. At these depths, the immense pressure of the surrounding seawater naturally forces water into the RO membranes. Since the pressure is already sufficient, there is no need for additional surface-based pumping systems to generate the required pressure. Desalination. Inside the membrane modules, freshwater permeates through the semi-permeable membranes, leaving behind concentrated brine, salt water with a higher salinity. This process is virtually identical to conventional RO, except that it is powered by ambient pressure instead of mechanical pumps. Recovery of freshwater. The freshwater, called permeate, collected within the module is then transferred back to the surface. This can be done using a low-energy pump or by using the buoyancy of a sealed freshwater return pipe, which allows the freshwater to rise naturally to a collection system on the surface vessel or platform. Advantages of deep-sea RO desalination. There are several significant potential benefits to this approach. Energy efficiency. By utilizing a natural hydrostatic pressure of the ocean, the system significantly reduces or even eliminates the need for high-pressure surface pumps, lowering energy consumption. Environmental benefits. Reduced energy requirements lead to lower greenhouse gas emissions, especially when paired with renewable energy sources for auxiliary systems. Reduced surface infrastructure. Since much of the desalination process takes place underwater, less surface space and equipment are required, making this system suitable for small islands or coastal communities with limited land. Potential for modular and scalable systems. Deep-sea RO systems can be designed in modular units that are easily deployed or scaled depending on freshwater demand. Challenges and limitations. Despite its promise, deep-sea reverse osmosis desalination faces several technical and logistical challenges. Maintenance and accessibility. Equipment located hundreds of meters underwater is difficult and costly to access for routine maintenance, inspection, or repairs. Membrane cleaning or replacement, common in traditional systems, becomes a major logistical issue. Biofouling and corrosion. The deep-sea environment is harsh, and prolonged exposure to high pressure, saltwater, and biological activity can degrade materials and foul membranes more rapidly than in surface systems. Freshwater transport. Bringing the freshwater from the deep sea to shore, especially over long distances, requires reliable and efficient pumping or flotation systems. This can introduce additional energy use or complexity. High initial costs. The materials, engineering, and deployment systems for operating under high-pressure deep-sea conditions are expensive, potentially limiting large-scale adoption in the near term. Environmental impact. While potentially less damaging than surface brine discharge, the impact of concentrated brine discharge at depth is not yet fully understood and could affect deep ocean ecosystems. Current development status. As of now, deep-sea RO desalination is primarily in the research and development phase, with some pilot projects and small-scale prototypes having been deployed. Countries like Japan and South Korea have been exploring this technology due to their proximity to deep ocean shelves and their need for sustainable desalination methods. However, it is not yet commercially widespread due to the aforementioned technical and cost challenges. Deep-sea reverse osmosis desalination is a promising but emerging technology that leverages natural ocean pressure to produce freshwater with potentially lower energy requirements than conventional methods. While it offers compelling environmental and logistical advantages, the complexity of deep-sea operation, combined with high upfront costs and technical hurdles, currently limits its widespread adoption. Continued research, engineering innovation, and environmental assessment will be critical for determining whether deep-sea RO can play a major role in future global water supply strategies.